Hello friends, welcome to Kion Lab. Today we are going to discuss closure of attribute set, which helps us in normalization to find out the key attributes, which in turn helps us to find out the functional dependencies in the given relation, and depending on that we are able to find out in which normal form the relation is, and we can resolve any type of redundancy present into the relation. Now what is closure of an attribute set? Given a set of attribute alpha, define the closure of alpha under F denoted by alpha plus as the set of attributes that are functionally determined by alpha under F. Algorithm to compute alpha plus the closure of an attribute alpha under F. Now given a relation R with attribute, so each attribute we are trying to find out its attribute closure. So attribute closure, it defines the set of functionally determined attributes. So if there is the functional dependency given in the relation A derives P, here for example I have two attributes A derives P, and the functional dependency is given A derives B, and if we are trying to find out the attribute closure attribute, that is this attribute or the this is the attribute. So this attribute of closure is the self attribute comes first and its dependent attribute. So B is functional dependent on A, so B comes here. B is going to add it into this attribute closure of a functional dependency. So algorithm is what? Result is equal to alpha. So this, in the resultant closure we are adding alpha into it. So similar like A closure, so A self attribute we are trying to add into that. So alpha plus I am trying to add. So self attribute gets added, just like here A we have added for a small example. We are going to see more examples in the coming slide. While changes to result do for each alpha derives gamma, that is gamma is dependent on alpha or gamma is derived from beta. In F do begin if B is the subset of result, then result is equal to result union gamma. Means this newly identified attribute which is functionally dependent on some another attribute, so that dependent attribute we are going to add in the resultant attribute closure here, just like that. So initially alpha gets added, sorry beta here, so alpha gets added here. We have found some dependency, functional dependency into the dependency set, that is F. F derives for functional dependency here F. So these are the functional dependencies given to us. For example, only one dependency, that is A to B. Then beta is the subset of result, then result is equal to result union R. Now here in our case beta, that is A is the subset of the result. So result is nothing but the attribute closure of a particular attribute. So A is my attribute and closure set. Closure means directly whatever the present functional dependencies into the functional dependency set, as well logically implies dependencies present into this F, which is not present. You have to derive from the Armstrong axioms rule, that is transitivity, augmentation, pseudo transitivity, union, then decomposition. So those rules, if you want to go through, you can refer my previous video, attribute closure of a functional dependencies, closure set of a functional dependency. That video you can refer. So from there it will be clear. So that logically implies dependency we can find out, and that attribute we are going to add here. So similarly here gamma, in our case gamma is nothing but a B that we are going to add or make the union, add into the closure set of a attribute. So example of attribute set, here I have the example A derives A, B, C, G, I, and this is the functional dependencies given to us. F, A derives B, A derives C, CG derives H, CG derives I, and B derives H. Now AG, this is the attribute that we would like to find out what are its attribute closure. So first attribute you can have in the resultant attribute, the same attribute, the self attribute we are going to add. So AG is there. Now next, A and G, these are the two different attributes here in the given relation. These are the two attributes A and G. So A, G, these are the different attributes. Now from A and G, find out what is the dependent variable. So here first one we have found out A derives B. So what we are trying to add here, A derives B as well A derives C. These two dependencies I have found out from the given first attribute. So what the algorithm told us, if it has been there dependency, so this dependent attribute we're going to add into the resultant attribute. So you can find out here in the resultant attribute C and B also gets added. So A and G initially were there and BC gets added because newly derived, and which is the part of the given functional dependency that is here. Now again what else is got added, CG derives H. Now here what do you found out, if CG is the subset of AGBC, CG is the subset, that is this attribute is present into my resultant, this result, that is the attribute closure, the subset, then whatever it is going to derive, it has been added, that is H is going to be added in the attribute closure set. Now next one, similarly CG derives I, that is also directly get added, CG derives I directly get added, and then B derives H because B is again a part of B derives H, again a part of attribute closure, so it is again added. Is AG is a candidate key? Now as per the definition of AG, is my candidate key or AG is a super key? What can be the answer? Now does AG derives R? Is AG R is the, it derives the minimal super key. R is a minimal super key. So if AG is my candidate key, so we are trying to find out whether AG derives all the attributes of the given relation R, then it can be a candidate key. But AG is not given to us, so AG is my super key. So here in the given relation R, AG is not the attribute which is going to derive, it is not the attribute that is totally going to derive a new attribute. So AG is a super key, and minimal of AG, that is A, is nothing but a candidate key. Is any subset of AG is a super key? Just try to find out. Any subset of AG, A is going to derive all the attributes, just check it out. A derives B, then A derives C, AG derives H, because C is derived from H, so we can replace C with A, so AG derives H. Similarly AG derives I and B derives H, so A can be a candidate key. Use of attribute closure. There are several usage of the attribute closure algorithm, that is testing for a super key, testing functional dependency, and computing closure of F. Now first, testing super key. Once you are able to find out whether this attribute derives all the attributes present in the given relation R, then that can be a candidate key. And if you could not find out any attribute which is going to derive all the attribute, one attribute is remaining, then you can combine that, augmenting along with that attribute, that is combining that attribute with the candidate key gives you all the attributes, so that would be called as the super key. Testing a functional dependency. Now once it has been found out the key attributes and non-key attributes. So if once we will get the super key or the candidate key, we can definitely distinguish between key attributes. So from the key attributes and non-key attributes, we are able to find out what type of functional dependency it will derive. So F will have the types of dependency: A derives B, B derives C, something like this, B derives C, something like this. Then suppose if we are able to find out A is my candidate key, then I can say key attributes derived non-key attributes. A is a key attribute and B is a non-key attribute. Then I can find out this is a full functionally dependent as per the definition of full functional dependency, and this is a partial dependency. So depending on that, we are able to find out what type of functional dependencies is this. Now to get to know all the types of functional dependencies present into the normalization, you can refer my types of functional dependencies video, and then computing closure of a F. So these are the usage of attribute closure. Now here we can see the example. This example also we have already referred in one of the video. So here I have these three functional dependencies, 1, 2 and 3. Now how do I get the closure set of the functional dependencies? I have S hash closure, CT closure and S hash P hash closure. Now first we'll try to find out S hash. So first of all we are adding the self attribute in that S hash. Second one, S hash derives CT status, so these two attributes gets added, CT status and CT derives status already is there. Now S hash P hash derives quantity. Now since this P hash is missing, this P hash we are not able to get in any of this whatever the dependency is given to us, so this is not going to further derived, and I'll get only these three attributes, S hash, CT and status. So since this attribute is not going to derive all the attributes which are present in the given relation, so only I have got S hash, CT and status. So this cannot be any key, not even candidate key or not a super key. Now CT derives status, self attribute we have, and one dependency we have found out, CT derives status, so we can add here status. We are not found out any dependency where we can get these two attributes, so this CT closure I'll get only two attributes. And the last one is S hash P hash closure. Now the self attribute S hash P hash, and from the given dependency it derives quantity, so quantity we can add. Now any other attribute can derive any other attributes from the given relation R. So here I have S hash derives CT status, so we can add this to CT status. Then this attribute I have got CT derives status. Already both the attributes are added into the final result and no more attributes remain. So this S hash P hash attribute closure, this combine, this closure derives all the attributes from the given relation R. S hash P hash CT derives quantity and status. So this S hash P hash, it acts as a candidate key. And key attributes and non-key attributes. So part of the key attribute, that is a candidate key, S hash P hash act as a key attribute, and rest of the attributes which are not the part of any of the keys, so they can act as a non-key attribute, CT, status and quantity. So this is one of the example we are able to find out the key attributes. So candidate key we have found out. Now depending on the key attributes, that is key attribute, part of the key attribute here, S hash P hash completely act as a candidate key, and this part of the candidate key is deriving non-key attributes. So CT status quantity non-key attribute, part of the candidate key. So this is called as a partial dependency. That you can see me, that this you can in detail get to know in the video types of the functional dependency. Now here non-key attribute derives non-key attribute. This comes under transitive dependency. And complete candidate key derive a non-key attribute. It can comes as a full dependency. So this will help us to find out the what type of dependencies present into the given relation. Now we can see one more example here. You can observe. Now again we are trying to find out the attribute closure. I have here some attributes s hash, s name, similar type of example, just what we have discussed, s hash and p hash. So similarly here what you can have, s hash derives s hash, self attribute s name. And here one thing you have observed, s name derives s hash, already added over here. Then s name derives s name and s hash. That's it. And s hash p hash derives s hash p hash, then quantity. S hash derives s name and s name derives s hash. So from this attribute closure, s hash p hash derives all the attributes present into the given relation are s hash p hash, s name and quantity. So this can act as a complete candidate key. S hash p hash combinedly act as a candidate key. And key attributes s hash p hash and non-key attributes s name, s hash p hash and non-key attribute s name and quantity. So now here to get to know the dependency part of the candidate key, because this complete candidate key s hash p hash, part of the candidate key derives s name. And here what do you observe? Part of the candidate key is present on right hand side. So this is called as overlapping candidate key. And this helps us to get to know the BCNF. And this is complete candidate key derives the non-key attribute. This is called as the full dependency. So this will help us, this overlapping candidate key helps us to get to know the BCNF. So this is all together what we have learned in the today's video, that is attribute closure set of in a functional dependency. So if you like my video, you can share the videos as well as you can subscribe it to get to know the upcoming videos. Thank you.